I'm Mac Rodriguez.
I'm Martina Heraldez.
I'm Peter Todd.
I'm Andrew Mickey.
I'm Charles Elliott.
I'm Jake Sekosky.
And this is how we made an interferometric microphone using a Michelson interferometer.
The Michelson interferometer is an optical instrument that uses division of amplitude to measure microscopic distances. It works by splitting a single laser into two paths with translatable and tiltable mirrors, which then recombine into one beam, causing interference upon their recombination. To turn this setup into a microphone, we simply replaced one of the mirrors with a reflective membrane that acted as an acoustic diaphragm, whose vibration due to sound waves directly correlated with measurable changes in the interference pattern. Our detector is then able to capture the oscillating light intensity and then convert it into a voltage signal that directly mirrors the audio waveform.
The spacing between fringes is inversely proportional to the frequency, meaning that the frequency itself is directly proportional to the velocity of the acoustic wave. Normally frequency would be a function of time, but since in this case we're making it constant, it leads to two changes. The first thing is that the phase shift itself is no longer a function of t either, and the second is that we can use a fast Fourier transform instead of a Fourier transform. Usually when frequency is a function, you can take the Fourier transform to compress it into a spectrum, and then the inverse Fourier transform to play it back into sound. However, since we don't have to worry about the frequency changing over an extended interval, we can instead run a MATLAB code to take the fast Fourier transform and its inverse, which is the Fourier transform over a small interval of time.
To explain our setup here, we first start with our helium neon laser into a beam splitter. This splits our path into two different directions. This first path we'll look at goes through a polarizer, off a mirror, back to the polarizer, and through the beam splitter. And this polarizer here is to attenuate our beam because this mirror is more reflective than our pellicle over here, so we want a similar intensity so we can detect the interference pattern. And then the path that goes through this hits a pellicle, and this oscillates with sound, changing the path length difference between these two paths. We recombine our signal to make an interference pattern. We expand it with this 25mm focal length mirror, and then we view it on our detector and we can record our signal. Then the signal from our photodetector comes to our photodetector amplifier, and then to our oscilloscope where we can see our signal versus time. As sound oscillates the pellicle and changes the path length, we change the interference pattern, and we can use this signal to reconstruct the audio.
So for our methods, we got the data off the oscilloscope, performed a fast Fourier transfer with a Hanning window on it, and reproduced the audio from the most prevalent frequencies. Similar analysis on the iPhone for comparison.
We had 440 plus 660 hertz for this one, 348 hertz, 772 hertz, 3000 hertz, and 631 hertz, which we also compared to the iPhone microphone.
So it performs comparably to a cell phone microphone, SNR in the 30 to 40 decibel range. Best performance is 700 to 1000 hertz range for the resonant frequency of the pellicle. We're able to reproduce the audio. Harmonics appear, but their presence is reduced with decreased source intensity.
Our greatest sources of error came from the time constraint of the oscilloscope at 5 milliseconds, the noisy room, the voltage responsivity, which wasn't included in iPhone data, and the varied position, which slightly changed our data each take.
Overall, we successfully constructed a Michelson interferometer using a pellicle as a sensing membrane and demonstrated that it could detect acoustic frequencies in the environment, which could be resolved with a computer. With our setup, we were able to visualize harmonics, identify tones through background noise showing strong signal-to-noise ratio, and measure frequency content across time using spectrograms. However, due to the limitations caused by our setup using an oscilloscope, it was unable to fully function as a traditional audio microphone. The scope's limited sampling rate and slow USB data transfer restricted us to incredibly short recordings of audio in the milliseconds at audio frequencies or longer, low bandwidth recordings. To improve the experiment, the oscilloscope could be replaced with an audio DAC or some other better acquisition device, both of which would allow continuous high frequency sampling and real-time audio playback, which would make for a better microphone.